Hello and welcome to Live from the Lab. This is the show where we talk about different technology that Bruker has developed to help scientists discover the world around us. Today's topic is orientation or texture analysis. Now when we talk about texture, we're not talking about the surface finish. This isn't whether it's velvety smooth or a hard surface, things like that. Rather, what texture has to do with is the orientation of the little crystals that make up the world. So when you think about a material, there's actually two ways it could be. In one case, it's a perfect single crystal, something like a diamond ring. That little diamond, all of the atoms perfectly aligned. The other end of the spectrum would be like sand on a beach, pointing in every single direction, those individual crystallites just kind of randomly oriented. Now, of course, most materials in the world, they exist somewhere in between. But the applications that we use them for, orientation can have some extreme effects on their macroscopic properties. Let's take an example that we all might know. Well, if we've flown on an airplane, you know those jet engines, they have those very, very big, spinning at fast RPM inside and very, very hot. Now inside of that jet engine, in that part, the combustion chamber, there's these little blades. They actually look like mini wings. And those mini wings, they are made out of a very special metal that can go to very high temperatures. Now when they actually make that metal, it's important that they have a single crystal-like texture. And the reason why is because when it's spinning at that very, very fast RPM, if it was like that sand on a beach, that material could actually completely just fall apart. So by making it out of a single crystal, that increases its ability to sustain in that environment. And there's many other examples, and we'll talk about a few of them today. So with that, we're going to go and actually see the analysis all the way from planning the measurement through executing the analysis and getting the result. So on with that. So I'm joined today by my colleague Jonathan.
John, thanks for having me on. Pleasure to be here.
All right, so today's topic, orientation analysis.
That's right. So preferred orientation analysis is becoming more prevalent as we try to push the boundaries for kind of performance and materials applications for engineered structural materials and things like the turbine blades and the engines that you're talking about. So it's important that we come up with a systematic method to understand texture in materials, and Bruker has been kind of one of the leaders in developing that. So what I have on my computer screen here is essentially an experimental measurement scheme that we planned in our software called DIFFRAC.TEXTURE. And you can see that essentially what we're doing is we're manipulating the sample in space, and as the diffraction vector aligns with the orientation of the crystallites, then we can determine whether or not we have random or preferred orientation. So as you can see here in the experiment that we've designed, and you can kind of play around with this depending on the material system that you're looking at, we essentially have these phi rotations in space here, and as you come out radially, we have, we're changing the sample tilt. So essentially we're modulating those parameters, and we're able to essentially map out what's called a pole figure in our sample orientation space. Okay. And that'll basically tell us whether or not we have preferred orientation or random distribution.
So maybe a little background for everybody. When you see these circle graphs, these polar coordinate graphs, they actually kind of have an interesting history. So X-ray diffraction, you know, we've always said that it's a multidisciplinary technique. It has been developed over the last 100 years. And geologists contributed quite a bit to the field. In fact, in terms of texture and orientation analysis, back in the day, what they used to do is they find these crystals, you know, in the cave, and they have, say, certain facets to them. And in order to try to understand that better, what they did is they developed this method where they built this hemisphere, and they had a little optic on it. And what you do is mount the crystal in the middle, and then look through the little optic, and you could actually determine the orientation of each face relative to each other. And so what you can imagine when you see these little graphs, you know, the circles, is it's just basically that hemisphere squished down. We call that a stereographic projection. There are other equal area and things like this projections, but that's often the word. But we also call it a pole figure. And when we say pole, we just mean that's the thing, the kind of the pole sticking out of the surface of one of those orientations. And while we're talking about this, I guess one other thing just to clear out, there are different coordinates too. There's the machine, or the goniometer coordinate system.
Right.
And what did you say those two were in this case?
You're looking at essentially the phi rotation of the sample.
So phi is rotation.
Yep. And then psi, which is your sample tilt.
Okay, so tilt of the sample.
Yep.
But then when we actually analyze the data, in the end, we're going to get a different set called the Euler coordinate system.
Right.
And this goes back to, again, the geological definition. And there we have phi 1, which will be the in-plane rotation, phi 2, which is going to be the tilt, and then we have another phi, which is going to be kind of the roll. A good way to think about it is kind of like aeronautics.
Yeah.
So with that interruption, sorry for interrupting you there, let's get back to this. So now we see these lines. What do the lines represent in that?
So the lines are taking advantage of our 2D detector technology. So with the Eiger, we can essentially look at using a spot beam. You get these diffraction cones that come off the sample, and instead of having to collect a lot of different data points at different sample tilts, we can actually use the whole 2D coverage to capture the Debye rings, which gets us the data in between those regions.
Okay, and if I had a more conventional diffractometer, maybe I don't have access to one of these 2D machines, what would this planning look like in that case?
So essentially, you would get rid of the lines in the pole figure here, and you would replace it with more dots in between.
Okay.
So essentially, yeah, to get the same coverage, the same data or similar data, that's what you would have to do. It would take a lot more time, but you could do it.
Okay, and what would we be talking about the time difference there?
You're talking about, you can see here in kind of what I've planned in my measurement, all three of these pole figures is going to take less than an hour.
Oh wow.
Yeah, so there's four, as you'll see in the analysis here, but essentially these three different types of measurements that represent different crystallographic reflections, right? Because we're looking at different crystal orientations, right?
Yeah.
As a function of these sample coordinates. But yeah, so essentially you're talking the order of an hour or less for this type of measurement. But in conventional techniques, you'd probably be looking at the order of multiple hours, if not days.
Oh wow. Yeah. Okay. So we've got the planning done.
Yes.
So now what would the next step be?
So we went ahead and collected this data, and we're now going to pull it into our analysis software called DIFFRAC.TEXTURE. It's developed in-house, specially designed for this application. And so when you're using our planning software, it actually becomes very easy to import the data. Essentially, it outputs it into multiple image files and then kind of one aggregated data set.
So you don't have to load all of the images, you just load the one file and it pulls everything in.
It intelligently aggregates the data in a way that is easy to understand and analyze.
And how many images were there about here?
Hundreds.
100, wow,
Yeah.
okay. So, and that was pretty quick, and you're just using a laptop.
That's right, yeah. So you can see the algorithms have been kind of streamlined, and with computational power these days, you know, it's a lot easier to do this type of stuff.
All right.
For a standard user. So you can see kind of how good the Eiger is in capturing multiple reflections in our sample. So now, again, this was coming from one of our measurement schemes, and we're able to collect more information because of the detector coverage. So now,
the Eiger then, that's this 0D, 1D, 2D detector.
Right.
And then here we're using it in a 2D mode.
Correct.
So it makes a picture. But when everybody's looking at that picture, what are kind of the coordinates here? So if we want to get familiar with that.
What we're looking at here, and a typical 0D or 1D would go along this axis here, which is the 2 theta axis. So here's 2 theta at like roughly 36 degrees. You could see kind of the angular coverage just by looking at this image, right, of the detector. And we go all the way up to beyond 47.
Oh wow, okay, all in one shot.
That's in one shot, exactly. And so in the direction perpendicular to that, we call that the gamma direction.
Okay, and then when we talk about Debye cones and stuff, this is like the Debye cone intersecting the detector.
Right.
Okay.
Yep.
Okay. And I noticed that like one of them looks kind of uniform, the one on the right, but the one on the left is a little brighter on the top, a little dimmer in the middle.
So that's basically what we're trying to characterize, right? So that indicates that we have different crystallographic orientations giving us more intensity in some regions of the ring and less in the others, which is basically texture.
So if this was like sand on the beach, more of those grains are pointing in certain directions, less in the other direction.
If it was sand on the beach, you would expect to see no difference in intensity along the ring.
Yep,
exactly.
So this is kind of slightly oriented sand on the beach.
Exactly.
Okay.
Yeah, there you go.
All right.
So to analyze this, again, very easy. Now we're going to basically define what our 2 theta ranges for each of the peaks that we're going to be looking at. So you can see I have the 1D integrated version on the bottom, which for me is a lot easier to look at. You can also look at the rings if that's kind of what you're interested in. But for me, I like to be able to see quantitatively what the background looks like. And if there's any shifting due to residual stress, I want to make sure that I have sufficient background on either side.
The important thing here would just be that we don't pick up any other peaks.
Correct.
You just get the one.
Correct, exactly.
Okay.
So you can see the first one just got pulled in pretty rapidly.
There we go. Okay.
So we're going to go ahead and perform this operation on the remainder of the peaks, and then we can take a look at what our pole figures look like for each reflection. So you can see it's very, very quick and easy to use, which we kind of emphasize here. So there you go. There's that one at 65 degrees. Okay. And as we go on to the higher angles.
One thing that just amazes me when you're doing this is how many images we're looking at and how quick this is going, even on a laptop. It's
yeah, I know. Every time I use it, it blows my mind.
Yeah.
And one thing that I don't know if I mentioned or not already, but this is an aluminum soda can that I've just cut up, basically. Yeah, we're looking at the sides of the can. So this has gone through many cold rolling and stamping and punching processes, right? Which can certainly affect the orientation or the preferred orientation in the sample.
And this so this is just regular old soda can. You just cut it out of the side.
That's it. Yeah, like a soda can that I'll probably have a can of soda for lunch. You could anybody can get a sample.
Okay, so if anybody back in their lab wants to try this out too, just go ahead, get a soda can. Maybe you can expense that, and
yeah, exactly.
There you go. Now you've got a perfect sample to follow along.
So if I go ahead and reorganize my window here, we can get a better look at what the data is telling us. So here are my 4 pole figures that correspond to each of my crystallographic reflections at each of the Bragg angles that we're looking at, right? So
now, why are they different? I mean, it's one material. Why don't they all show the same pattern?
Essentially, you have these 2 different types of symmetry in your material, right?
Okay.
You have crystallographic symmetry, which is dependent on the crystal structure. In this case, we're looking at single-phase aluminum. Okay. And you also have process symmetry. Mm-hmm. So the process symmetry is going to essentially change what the pole figures look like. And if we go ahead and index them. So again, we have a kind of our own material database. You can go ahead and import materials into here.
Okay. So you just bring that in.
That's it. It just automatically indexes the pole figures. So essentially, by looking at these reflections now, I can say, okay, well, if I pull my mouse over here, I have greater than random orientation at an angle at a tilt of 24 degrees and rotation of 180 degrees. I also have that at 0 here.
Okay, and when we see these numbers, you had mentioned indexing.
Right.
If this was a cube, I'm not sure if aluminum is a cube, but
it's face-centered cubic crystal.
Oh, okay. Okay.
Yeah,
so it is a cube. Yeah. So then when we see numbers like 1, 1, 1, what does that mean?
So those are the reflections. So right, diffraction, you get the despacing between the planes, right?
Okay, so it's the atomic plane. So we have this cube, face-centered, so it has an atom in each face and an atom in each corner. Yep. So 1, 1, 1 would be which plane? It
would be the plane that corresponds to the, essentially you can imagine you have this cube, right? Yeah. And if you put on X, Y, and Z, if you put a point on X equals 1, Y equals 1, and Z equals 1, connecting all of them.
So kind of this body diagonal.
Exactly,
okay. And then if we had something like a 100, that would actually be the face.
Exactly. Yep.
Okay.
Yep.
All right.
So that would be the diffraction. You'd be diffracting off of those types of planes.
Okay. Right? And each of these planes is going to give us different information about the orientation. So even though we're not capturing the whole pole figure, we in essence do have all of the information encoded.
Right. Exactly.
Okay. So I guess the next step would be to somehow combine that information into a single model, right?
Right, exactly.
All right.
So we have 2 different analysis techniques. One's the spherical harmonic method, which is basically just a series expansion that'll fit your data. Mm-hmm. And then we have the component method, which is kind of a newer technique. And this is where you're basically defining different components on the user's part, and then that kind of explains the texture. the material.
And the way I like to think about it, so spherical harmonics, that's actually a math that was developed during the kind of quantum era of science, when they were thinking about orbital theories of electrons and things like that. So basically, they made these shapes. Some of them look like ice cream cones. Some of them look like donuts. Some of them are combinations of these things. And back when they were thinking about texture, they said, you know what? If we flatten those out, kind of reminds us of the pictures that we're getting.
Yeah.
And then if we can add different orders of that, as we add more and more of these components to it, these spherical harmonic components, it fits it pretty well. So it's basically a mathematical approach to fitting this texture. On the other hand, the method of components was developed more of a material science route, where we said, let's start with the actual materials.
Right.
And let's assume that one is pointing this way and one is pointing that way, and then let's regress that against the raw data. So those are the two kind of differences. So spherical harmonics, though, that's pretty simple to do, right?
It is. It's a couple of clicks in our software. I'm going to go ahead and pull it up right now, since we have our peaks indexed here and our pole figures, experimental pole figures created. So, you know, again, you can see everything's kind of accessible in the upper panel here. This is component method. I just selected the harmonic method. So you can see, you know, kind of your different selections here for the sample, you know, what we call process symmetry. So this kind of requires you to have some understanding of how your material was made and what kind of symmetry you expect. And you can kind of infer that from the experimental pole figures as well.
Now, you had said, though, that this is a cubic material, crystal.
That's right.
But I don't notice that cubic is in there.
Right. So the I mean, we've defined the crystal structure, which is from the material database, as aluminum, and that's FCC, right?
Okay.
But the process symmetry here, this is basically just turning on different symmetries or not, right? So triclinic would give us total flexibility to be able to fit something that we don't necessarily know the process symmetry of. In this case, I'm going to kind of cheat a little bit and go monoclinic, because I know that we have some symmetry in the system.
Okay, so it's basically like it's the symmetry in the graph, not the symmetry of the crystal.
Correct.
So if we did triclinic, it's like kind of Hail Mary,
right,
whatever. Orthorhombic, on the other hand, that means like you look at it and you kind of go, you know what? It kind of looks the same in all four quadrants.
Yep, exactly.
And that's going to lock it down a little bit.
Yeah, exactly. So it just has to do with the symmetry of the system. And it's very easy to just play around with it and demonstrate that too. And you'll see it in the calculated pole figures.
All right.
Yeah.
All right.
So I've played around with this a little bit, and I found that typically for these types of textures, I like a lower rank in expansion.
Okay.
Otherwise, we tend to get oscillations in the data.
Kind of overfitting.
Exactly.
If you do too many, then you're overfitting.
So, and then I'm going to turn on positivity refinement, which just turns all of our coefficients on to positive values.
So they can't go negative, which is kind of a reality constraint.
Exactly.
Okay.
Yep. So then all we do is go ahead and click OK. And it's going to run the evaluation.
So I imagine this is now going to take a little bit of a while.
Well, you'd be surprised, John.
Wow. Okay.
So it actually is able to pull in the data very quickly, analyze it, and spit it out into our recalculated pole figures. So you can still see that these are the incomplete versions, right? But the data actually looks like it coincides pretty well with the experimental measurements.
Yeah, I mean, there's like, I see some subtle differences between them, but really we've captured the essence of it, you know, and that quickly. I imagine if we increase components or, you know, play with that a little bit,
you can definitely get a better fit, for sure. Yeah. But you can kind of characterize that using the difference pole figures on the right here.
Okay.
You know, what the differences are in my fit versus how well it, you know, calculated using the harmonic method.
But the important thing is to capture the major features of what's going on.
Exactly.
All right. And then is this the result, or?
So there's a lot of different ways that we can look at this data. For one, we go ahead and the software will automatically calculate the orientation distribution function, which is, like you said, those three angles.
Wow.
That relate,
say that 3 times fast.
Yeah,
right?
exactly.
I will. ODF.
Yeah. So essentially, this is a characterization of what kind of rotation we have to apply to the crystal symmetry to get it in line with the process symmetry.
Okay, so the way I like to think of this is actually a cube. This is a cube, or it's a rectangular object, like a box. And in one direction, we have that in-plane rotation. These are Euler angles. The next one, we're going to have the tilt. And then in the final one, we have the kind of roll around that vector, and those are the three. Those would be the 3 axes. And that's what we're seeing here. And it's called ODF because it's actually a distribution function.
Yep.
So it's continuous.
Yep.
Right, for orientations. All right, so does this mean something?
It does, yeah. So we have a few spherical components here, and what this actually allows you to do, it's basically a characterization of the total orientation of the crystallites in the sample.
Okay.
So from this, we can actually calculate new pole figures.
Ah, okay.
And so you can see, based on the fitting, we were able to fill in the regions and create our complete pole figures. So again, here, what we see with the 1-1-1 reflection is that we have kind of preferred orientation in the rolling direction.
Yep.
Another way to look at this data, which is simpler in my mind, is to go to the inverse pole figures.
Okay.
And this essentially tells you now what directions do I have these different reflections, giving me preferred orientation.
Yeah,
right?
I mean, the thin film grower in me sees pole figures and goes, yeah, that's what I want to see.
Yeah,
and then
exactly.
the metallurgist in me says, nope, inverse, because rolling direction is in the process direction, transverse would be the other direction in the plane, and then normal is out of the surface.
That's correct,
right? So
you can see here, we have 1-1-1 preferred orientation in the rolling direction, transverse is 1-1-0 or 101, and then normal direction also a little 101.
Okay, so this is, so what's kind of nice then is that you can get all of these different things depending on what your need is, right, in your specific application.
Yep, exactly.
So that's pretty much it to analysis, right? I mean, we just kind of look at it qualitatively and...
Well, actually, so there's another method that we can use if we want to get more quantification and actually get volume fractions of individual components in our sample. So the harmonic method is very good for like a quick overall analysis. If it kind of treats everything as a single system, right? With the component method, we can break it up and get more quantitative information from it.
Okay, yeah, and it gives us that complete pole figure really quickly, which is nice because it's hard to get that. I mean, we can't see the whole thing because of sample shading and things like that. There are other methods like in-plane diffraction. You can certainly try to get the outside portion of the pole figure, but not every sample is suitable for that. So this is just a really quick, easy method. So now we're going to go to, you had said component method.
That's right. That's the one. So that's right up here again, kind of come back home. This is like your home base.
So we don't have to start over from scratch. We don't have to just import
data? We're just
data?
adding it over into the data tree. It's going to use it. It's intelligent enough to know that we're going to use the same data.
Okay.
So essentially all I need to do is go ahead and click component method here. And it's going to ask you, all right, for which reflections do you want to apply this analysis to? I'm going to use all the data, right?
Why not?
The more the merrier.
Yeah. And by the way, if anybody has questions, go ahead, type those into the chat window on the side there of YouTube, and we'll get to those at the end.
So now you see I'm in component mode here?
Yes.
All right, so essentially, now what we're going to do is click on these high points here, but first we have to define what our process symmetry is, right?
Yes, because right now in the middle column we are seeing a very terrible fit.
Yes, so this is actually random orientation in the middle right now.
Okay, so just nothing. Or nothing or everything.
Right, exactly.
Right? Okay, everywhere.
So I'm going to apply kind of the same process symmetry that we used prior.
Okay.
And then I'm going to click on the high point here where we see preferred orientation. And you can actually see, if I change the process symmetry, how that affects the symmetry of where my expected poles are going to be.
Okay, so when you're putting it in, it's actually taking a crystal and adding it to your sample.
Exactly.
And now with triclinic, we only added one crystal, but when you add monoclinic, it's actually like adding a second crystal that's in the opposite direction.
Exactly.
Okay.
Yep. So then we can go ahead and add this and then fit it. And we should see a difference in our recalculated pole figure. Hang on one second, I might have to add it again.
And when you're adding components like this, there are different types of components. So the most basic one is something called a spherical component. This would be basically like a single crystal orientation with a broadening. The other one is called a fiber, and a fiber means we're going to add that component and it's like a single crystal in one way, but in the other way it's completely random, so it's like a circle. And then in a new build coming out soon, what we're going to do is add in what's called an elliptical component. And this is kind of like that single crystal one, but it has 3 different factors for each direction of broadening. So if you have things that are kind of like, kind of oriented, but they have one direction or 2 directions that are meaningful, then that starts to, that'll help with those issues. Right now, the way you'd approach that is just to add multiple spherical components. So it looks like, though, we're starting to build up that fit pretty well here.
That's right, yeah. So you can see how I've only added 1 component.
And the first one looks, I mean, I see those basic things, but now we start looking at the next one.
Yeah, you can see that there's some differences here, and this is really where the difference pole figures come in handy.
Yeah.
Because we know that there's more than just this one component. And we can go ahead and just click on the difference pole figure now and add that as a component.
Okay, so you just add in another one.
Yep, exactly. So now you can see how that all changes, and we're building up this other component.
Yeah, so we're starting to fill in that region where it's a little, you know, dimmer.
Yeah, exactly.
Okay. Still not perfect.
No, it's still not perfect. So you can see we can keep adding as many components as we want.
Okay.
So I'm going to go ahead and add that one.
Okay. And you're just kind of looking at that difference one to hit the big differentials.
Exactly.
At this point. Okay. Oh, wow.
Yep.
Now that really, I think, started to fill it in quite a bit.
Yep, exactly. So we can keep doing this, and you can see how much more, I guess, coincident that the recalculated pole figures are relative to the experimental ones.
Okay, but now that we've added them, we can also refine them all at the same time, right?
Yes, exactly.
Okay. So, because it looks like we've gotten most of those structures, most of the major things, we've kind of that dog bony shape, and that. So maybe it's time to hit the go button, or what do you think? Or do we got to add more?
If we hit start optimization, so actually what I was doing is
I guess
this
is going to take a while because you were like,
So
wait.
Actually, what I was doing is I was adding the components and optimizing them at the same time.
Oh, okay. Okay.
Yeah.
Okay.
So I think we're going to need to add at least 1 more component.
All right.
To get a better picture here. So I'm just going to go, well, let's see what this gives us.
And I noticed that you could also analytically type the numbers in, or quantitatively,
you can, and you can actually, if you don't want those numbers to be refined, you can fix them here by just, checking the check boxes.
Okay.
I like to let everything float.
Yep.
That's just,
And and one other feature too is if you have a standard texture, like a Gauss texture, rolling texture, you can actually just bring in that whole component as a single.
All right, so if I add 1 more.
I guess this is one of those things where you just keep going and going and going.
You can, yeah. So I like that one, especially when you're looking at texture like rolling that's very complex.
Okay.
That has multiple components to it. There we go. Now you can see this one here with the 200 reflection.
Yeah, you get that kind of rectangle.
Yep, exactly.
All right. And so now what information are we getting then about these components now?
So if we take a look at kind of the tabs down here, you can see your component pole figures.
Yep.
You can see kind of 3D visualization of the orientation.
Of the individual component.
Correct.
So that's saying there's a lot of grains pointing like this.
Exactly.
And if you pick a different one,
it'll
then
show
it's
up
gonna...
differently. Exactly.
Ah, okay.
Yep.
Then it says now it's pointing this way.
Yep.
And then it also tells us the fraction of each, it looks like, right?
So if we take a look, we just go ahead and click volume fraction over here, it'll tell us, how much of what component is in my sample.
Okay, and in this case, it looks fairly uniform. And I imagine if any of those kind of go towards 0, it's like,
it's probably we don't need that one.
Yeah, we just get rid of that one.
Yeah.
Okay.
And that can happen if there's some type of spherical broadening or anything like that, right?
Okay.
So, and again, so now let's say we have our analysis complete over here with the component method. I can come down here, ODF, very similar to what we had prior, right?
Yeah.
I mean, if we compare these things, you get a little bit more noise with the harmonics. And you can see this brings it out to 360 degrees as opposed to 180.
Yeah, so the big difference there, right, is that this is more quantitative, and we're actually fitting and regressing this model, this model of like a certain number of components, and that's why the background is much better.
Yep.
One other thing to note, though, we did talk about spheres, and we talked about fibers, and even ellipses a little bit, and that's actually where the name comes from. The name actually comes from the ODF. If we were to look at this in 3D space, spherical component actually looks like a sphere.
Yep.
And a fiber component will look like a fiber. So that's the names, where they actually come from.
So then you can see there's nothing in calculated pole figures. We can go ahead and add whatever we want, though, now that we have the ODF. So if I add a new pole figure, let's just do 1, 1, 1.
Oh.
So let's just say not 10. We do 1, 1, 1, and add that.
Okay, so you can build, because now that you have this sample model, it can then go back and say,
exactly.
I can calculate any pole figure.
That's exactly right, yeah.
Right.
And then you can see inverse, same exact thing. I mean, the consistency in the results is pretty good as well. So you can see, again, we have that 1, 1, 1 rolling direction texture. We have the 101 and transverse. You see that in both cases. Yeah. And the same thing, 101 normal direction.
Right, right. But here, what really strikes me is how much clearer I can see that in, for example, the normal direction, it's going from 101 to 112.
Yep.
About. So that really cleans it up quite a bit. A little bit of extra effort, but I think that you get extra. It's definitely worth that.
Yeah. So the spherical harmonics method was kind of the legacy method, right?
Yeah.
From what I understand. Yeah.
So we're getting around to the end of Live from the Lab. I did want to mention though there is a pretty nice report method in here.
Yes,
like a report maker.
So if we go to, I mean, you can print this stuff out. You can export. If you want the raw data, you can go ahead and export pole figures, right? So you can do the same thing with all the ODFs and the coefficients used to calculate the data. So you can get it all out, and like I said, there's also actually, it makes a nice standard report if you're in industry and you're just looking for a standard report. So with that, I think we're going to get to a few questions. Again, if you have that question right now, let's go ahead and type it into YouTube. Otherwise, if we don't get to it, or you want to ask it later, maybe you're viewing this later, go ahead and send it to live.events@brooker.com, and we will respond to those questions. So to get over to the questions that are coming live, first of all, from Marty, is there a limit to the size of the object? Well,
can I measure an engine block? Right?
Yeah, right. I mean, it depends on how big your diffractometer is.
That would be true. Right? Yeah. So
generally, you're looking at, when you're employing texture measurements, you're looking at a spot on your sample, right? So you're employing a parallel spot beam. Typically, in this case, I think it was a millimeter diameter spot beam, right? So your samples, it's not advantageous for them to be that large.
Okay, so if it's basically whatever you can fit on there, and we do have to think we are tilting the sample, so really look at what's the weight limit on your stage 2.
Right.
Just because it fits doesn't mean that it stays in the center of the machine.
Yeah, if you're doing any manipulation like that,
Yep. And with that note too, we have to think about shadowing. Like if you have something with a kind of a rough surface, a complex shape, that's going to do something, right?
Right, exactly. If you tilt your sample too much, your beam can fall off. There's a lot of things that can go wrong, which is why, letting the software do the work for you is kind of helpful. So you can,
Yep. So next question that came in from Xiaodong is why the calculated pole figure looks smaller than the measured pole figure. So if we look back at one of the calculated pole figures.
Let's see, we got these guys, or you're talking about the experimental then calculated.
That could be, maybe that's.
Let's see.
Let's look at that window maybe where we saw that too. Yeah, it kind of looks maybe a little bit smaller there.
It does, yeah. I am not 100% sure about that one.
It could be masking, or it could be. I wonder if we have if you right-click on it, we might be able to check what the projections are. Or no, it's not there. It's a very good question. It does look a little bit smaller.
Yeah, though, it does. I don't know if there's any significance to that or not. But,
so we'll look into that a little bit. It could be that in the modeling or in one of the settings, we actually have some sort of a setting to remove the very edges. Sometimes the edges can actually give you
What's interesting is you don't see that really in the component method. Do you see it here?
No, I don't.
So it might just have to do with the calculations with the spherical harmonics.
Yeah, sometimes in the harmonic method, if you actually overcalculate the edges in particular, you can get some odd perturbations.
There you go.
So I'm guessing that's what that is. The next question, can you explain how to set up a texture measurement in Wizard?
Yeah, so if we kind of go back to my Wizard example,
Yes.
It's pretty easy to do. I'm not in front of the instrument right now, so I can't do this live.
So this would be in your DIFFRAC.measurement software. You have all the tabs, and you just click on Wizard, and then you click File, New, and you can choose a texture.
Yep, exactly.
So, and then from there, what do we do?
So from there, we can go ahead and import, our current instrument configuration in DaVinci, which is kind of our system where, the system's kind of self-aware.
So DaVinci would show you how the machine's currently configured, but if you want, you could also say require it to have certain slits. And things
especially
like
if you're going to be running with a 2D detector.
Yeah.
You want to open that thing up, right?
Yep,
So,
change the settings. Even change the distance. Now, what is the optimal distance for this measurement?
Great question.
In terms of a detector?
In cases where you're not too worried about instrument, peak resolution, things like that, which is in a lot of cases with polycrystalline metals, right? I prefer to push the detector as close as possible, so then we don't need to capture as many regions of the rings. Their rings are effectively smaller, closer to the sample. Right?
Yeah, so if you put it really close, you're going to get a lot of coverage. I mean, you can get something like 20, 40 degrees of 2 theta in one shot, and that also gives you more of the angular coverage.
Right, yeah, exactly. So you can see at lower angles here, I don't have to take as many of these size steps, right? Because as you go to higher angles, your rings are bigger.
But we do need enough resolution to separate the peaks of this phase, but also think about if there's any other phases present. We need to make sure we have that amount of resolution.
Exactly, right.
So that was kind of DaVinci. Then the next step was...
the next step you would go into Texture Basic, and you would design your experiment for each reflection with the pole figure that you want. So you'd have to have some knowledge of where you're expecting crystallographic reflections.
And if you don't know where those peaks should be?
If you don't know, if you know nothing about your material, you can do a simple powder scan. That'll give you some idea. Again, if you do have preferred orientation, you might miss a couple of peaks, but... So you can kind of gauge based on that, and then once you find the peaks you're interested in that you want to look at, for a pole figure, you just throw that right into the software. You can see I've set my 2 theta HKLs as where I'm expecting these types of reflections, right? And then kind of cleverly in the middle of those two other ones, so I can capture both peaks with one snapshot, which is nice.
So a little thoughtfulness there can save you a lot of time, and definitely I like that idea. You do that powder scan, and here's another tip: if you have something that's pretty textured, go ahead and set it up with the point beam. Use the 2D detector, and then actually rotate the sample and oscillate your psi while collecting that scan. When you bring it into EVA, you're basically kind of making a powder out of it. So now you can do your phase ID, bam, you get all of your peaks, you know exactly what coverage you got, and you're ready to go.
Exactly. And again, the coverage here is solely up to what you're interested in, and what kind of resolution you want in the pole figure space.
So each of those lines in the top of the table, that's going to be one set of measurements.
Correct.
Right?
So these are, exactly 3 different measurements, and you can see that the spacing, I try to keep pretty consistent between the rotations of the sample.
So you want a little bit of overlap for the 2D detector.
Because you don't want to miss any information, but you don't want too much where then you're just wasting collection time. So you can kind of see how that I've designed that here, right? So you can see how they're kind of touching but not overlapping. So
and if you had a point detector, it would be very similar, just not the lines. You would be putting in a lot finer steps there.
Exactly. So you can see at the higher angle we get even less coverage because we're looking at much bigger rings. So after you do that, you would just kind of export this. You want to update your drives first. So I always tell everybody, make sure you update your drives.
And that's so that it's at the right X, Y, and Z.
Exactly. So your sample's in alignment and everything when you've done that in Commander. Then you kind of go over to start jobs, and you can add that to the job list, and it'll go ahead and start the measurement for you. And then again, very easy to import that into DIFFRAC.TEXTURE to analyze the data.
And while it's running, you can look at the measurement tab or the Commander tab, and you'll see it collecting, and you can kind of monitor the progress.
One thing that I always like to do as well is take a 2D snapshot before you go ahead and design the experiment. This way you know how long do I need to capture for to get enough intensity.
Good signal to noise. So next one, how to measure the texture of a 50 nanometer polycrystalline thin film.
There are, I think, somebody that I work with that has looked at grazing incidence pole figures.
Yes.
It's not something that I've done personally.
Yep. So actually 50 nanometers in the thin film realm, it's not the thinnest thing ever. When I think about really thin, atomically thin, 3, 4
Right.
nanometers, okay, then we might have to look at grazing incidence methods to really up the game in terms of intensity. Even then, by the way, if you have a good epi film, not a problem. Now 50 nanometers, yeah, I would expect the signal is going to be a little bit lower. But what you have going for you is oftentimes those films will have stronger orientation. And in that regard, you're going to get a little bit better signal. So go ahead, just stick it in there, do the same method that we were talking about here, and you're going to be just fine in terms of getting that result. One other tip, though, whenever we talk about films, if it has a very strong texture to it, make sure when you do those steps in the rotation angle, phi, that we're going to use a finer step so that we don't walk right over the peak.
Right.
Because you could do that if it's a really sharp epi peak and you've got a really sharp beam coming in. But otherwise, 50 nanometers, actually, to me, it's not thick, but it's not of the thinnest variety there. So, and thank you to Zhao Dong for that question and Shri for the previous one. Next question from ND is, do you need the space group for pole figure analysis?
Well, the space group is basically defined by the crystal structure, right?
Yes.
So that is kind of automatically included into the software when you import the crystal.
Yep. So when you are indexing it, indexing the pole figures. Now to make the pole figure, I guess the answer would be no.
Right.
To just make the pole figures themselves, that first step, no, you don't.
No.
But if you want to do the analysis, we need to know how each reflection relates.
Exactly.
So yes, in that case, you would need to know the space group. So go ahead, do your powder scan, get your result there. You'll be able to get it right from the databases, right? And by the way, another question, or another answer that we just got in from Kurt Erlacher. He's actually one of our scientists over in Germany. Thank you for answering that. This is, with respect to that coverage, is that the calculated pole figure coverage is given by the chi limit that is shown in the harmonic method. The default value represents the lowest measured chi value of all pole figures. So it is just a setting that you can change in the software. That's why it was being limited. And thank you to Kurt for that question. Now, we do have another question here that had come in. And that question is from Elizabeth. Do I need any special parts on my machine to do this?
Well, you need kind of your standard X-ray diffractometer. As long,
so we have an X-ray tube. We have a detector.
Yep.
What about the stage?
The stage has to be able to manipulate the sample in space, though. That's kind of the main thing, right? And you need a spot beam.
Yeah. So I would say the recommended or the normal way of doing this is going to be spot beam, stage that can tilt.
Yep.
Like we call it a cradle. So it tilts, rotates.
Yep.
Right. There are ways that you can do texture analysis without that. You can do it just with rotation.
Yep, and then iso inclination, where you're kind of rocking the arms to
and even a line
tilt.
beam you can use in some way. But the 95, 98% of people, that's going to be, you want that cradle, it's called, and there are ones, smaller cradles for smaller machines, bigger ones for bigger machines. And then a spot beam somehow.
Yeah.
Point beam. And then one more question here. Last question from Robert. How long does this all take? So how long does a scan normally take?
Well, you saw how the analysis takes less than a half hour.
Yeah,
right?
So and I was really astounded actually at how quickly even just your laptop, like this stuff wasn't pre-done, right? Like you were doing it here live.
No, this is all rendered right here. Yeah.
Okay.
Yep, and live. Yeah.
So how long does the actual scans take?
So the scans take.
I mean, come on, you got like a lot of rotations,
there's a lot
of tilts.
There's a lot of data in these pole figures.
Yeah,
it's true.
Yeah.
So the scans that I don't know if you can. You guys can't see my screen anymore, but all three of these took, as you can see in Wizard, less than an hour, right up here.
An hour?
Yeah, less than an hour. Under an hour to collect this because we're taking full advantage of the
Man, I
Eiger.
remember taking like one pole back in the day, when I was young and we had a point detector. In order to get one pole figure with the two background pole figures, it would take us like a whole day.
Yeah,
for just one.
Exactly. I know, right? That's kind
of
that's the old-fashioned way. Now with these 2D detectors, you can collect a lot more data. Takes a lot less time. Everybody's happy.
Yeah, you know? That's right. And you get free reflections too sometimes, right?
Exactly.
Because they all fit in there. So with that, I would like to thank Jonathan for joining me today.
John, thanks for having me on.
Yeah, and thank you all for joining us today and spending your time. And with that, until next time, let's keep your signal high and your background low.